So, you've probably heard a lot about quantum computing, right? It sounds like something straight out of science fiction. Well, today we're going to demystify it. Think of this as your personal roadmap into one of the most revolutionary fields out there. We're going to figure out what it is, how it works, and, where this whole crazy technology is actually going. Let's jump right in. Okay, so our journey is broken down into 5 main parts. First up, we're taking the quantum leap. We got to get our heads around the totally weird rules of this new world. Then we'll open up the quantum toolkit to see how we can actually build things with these rules. After that, we get to the really cool part, the killer algorithms, and you'll see just what they're capable of. Then we'll have to face reality with the noise problem. It's the single biggest challenge in this field. And to wrap it all up, we'll look ahead to the AI frontier, where things get really interesting. All right, first things first, we absolutely have to get one thing straight. A quantum computer is not just a souped-up version of your laptop. Not even close. We're talking about a completely different kind of reality, one that plays by a whole new set of rules. So let's break that down. You know the computer you're using right now? It runs on what we call classical bits. Just think of them as simple light switches. They're either on or they're off, a 1 or a 0. Super predictable. But a quantum bit, or what we call a qubit, that's a whole different beast. It doesn't have to choose. A qubit can be a 0, it can be a 1, or, and this is where your brain starts to melt a little, it can be both at the exact same time. It's all about probability. Okay, so let's get a tiny bit more formal for a second. The qubit is the fundamental building block here. And even though we talk about it being a 0 or a 1, its actual state is way more complex. Physicists have this cool way of visualizing it. They imagine it as a point on the surface of a sphere, which they call the Bloch sphere. So instead of a simple on-off switch, it's more like a tiny dial that you can point in literally any direction. But wait, how can something be both a 0 and a 1? Well, this is thanks to a mind-bending principle called superposition. The best way to think about it is like a spinning coin, right? While it's up in the air, tumbling around, is it heads or tails? It's neither. It's kind of both possibilities at once. It's only when it hits the table, or in our case, when we measure the qubit, that it's forced to pick one, heads or tails, 0 or 1. And that ability to hold all those possibilities in the air at once is the secret sauce. That's where all the power comes from. And just when you thought it couldn't get any weirder, we have entanglement. This is the one that even Einstein had trouble with. He famously called it spooky action at a distance. So imagine you have 2 of our spinning coins, but this time they're magically linked. The second one of them lands on heads, you instantly know the other one, no matter how far away it is, across the universe, is tails. It's like they're not 2 separate things anymore, but one single system that shares the same fate. Spooky is right. Okay, so superposition, entanglement, this is all pretty out there, right? It sounds more like philosophy than engineering. Which brings up the big question, how on earth do we actually control this stuff? How do we take all this quantum weirdness and, build something useful with it? And that question leads us perfectly into our next section, because to build with these quantum rules, you need a whole new toolkit. We're talking a new language, new tools, a new way of thinking to put all this strangeness to work for us. Now, the language of quantum computing is basically math. Specifically, it's linear algebra, which happens to be perfect for this kind of work. You can think of it like this. We use one part of the math to describe the state of our qubit, like where exactly our little dial is pointing. And we use another part of the math to describe the actions we take, the things that actually turn that dial. This math is literally the instruction manual for controlling the quantum world. So when you actually run a quantum computation, it's a surprisingly straightforward 3-step process. First, you get everything ready. You initialize your qubits, which just means you set them all to a known starting point, usually just all zeros. Step 2, you do the real work. You apply a sequence of what are called quantum gates. These are the operations that actually manipulate the qubits, putting them into superposition and entangling them. And finally, step 3, you measure the result. This is the moment where you force all those spinning coins to land, collapsing them into a final answer of plain old zeros and ones that we can read.
Okay, so we've got the concepts, we've got the tools. But what's the payoff? Why are we going through all this trouble? What can a quantum computer actually do? This is where we get to the mind-blowing stuff.
Well, it turns out there are a few killer algorithms that really show off what these machines are capable of. Take Grover's algorithm. It can search through a gigantic, totally disorganized pile of data way, way faster than a normal computer ever could. But the one everyone talks about, the really famous one, is Shor's algorithm.
This is the one that could, in theory, break a lot of the encryption we rely on every single day. It does that by factoring enormous numbers at speeds that are just unbelievable.
And I really want you to just look at these numbers for a second. Let this sink in. Factoring a big number, the kind used for online security, a classical supercomputer would need billions of years. That's older than the Earth. A quantum computer could, theoretically, do it in a few hours. This isn't just a little bit faster. It's a fundamental, game-changing leap. The scale of this is just, it's hard to even wrap your head around. Okay, so before we all get too excited and start planning for the quantum future, we need a reality check. We have to talk about the massive, huge obstacle that's standing in the way of all this. It's the one great challenge that everyone in this field is fighting against. And that challenge comes down to one simple, brutal fact. Quantum states are ridiculously fragile. I mean, the slightest little vibration, a tiny fluctuation in temperature, any interaction with the outside world, and poof, the whole computation is gone. It's like trying to build a house of cards in the middle of a hurricane. This fragility really boils down to a couple of things. The first is noise. Think of this as any and all interference from the environment. Heat, vibrations, stray magnetic fields, anything that can knock a qubit off course. All that noise leads to decoherence. That's the moment a qubit just gives up. It loses its special quantum powers and collapses into a boring old classical bit, which completely wrecks the calculation. So the ultimate goal, the holy grail, is error correction. But how do you fix an error on a qubit without looking at it and accidentally destroying the whole thing? Yeah, it's one of the toughest engineering problems on the planet. And all of this brings us to right now, today. We are currently living in what's called the NISQ era. It stands for Noisy Intermediate Scale Quantum. And what that really means is, yeah, we can build machines with a respectable number of qubits, maybe 50, maybe a few hundred, but they're just too darn noisy and unstable to run those huge, game-changing algorithms like Shor's. Not yet, anyway. We're in this really critical, messy, experimental stage of building this technology. But you know what? This story absolutely does not end with those challenges. In fact, maybe the most exciting part of this whole field is where we're headed next. People are looking to the future and imagining what happens when you combine quantum with another world-changing technology. And that next revolution is quantum machine learning, or QML. This is it. This is the big idea. What if you could fuse the raw computational power of quantum with the learning ability of AI? The goal is to tackle problems that are just completely out of reach for either one of them on their own. One of the coolest techniques for doing this is called a variational quantum circuit. It's a really smart hybrid model that's perfect for the noisy computers we have today. Basically, you let the quantum computer do what it's good at, exploring a whole bunch of possibilities. Then you hand the results over to a normal classical computer, which analyzes them and tells the quantum computer, okay, try tweaking it this way. It's like a feedback loop, a teamwork approach where each computer plays to its own strengths. And this whole idea, this fusion, is kicking off entirely new areas of research. You have brilliant people trying to figure out how do we even represent complex real-world data in a quantum system. Others are using quantum machines to spot incredibly subtle patterns in data that a classical computer would just never see. And some are going all in, trying to build totally new kinds of AI, quantum neural networks that are based on quantum physics from the very beginning. So this is where we're at, standing right on the edge of a brand new frontier. The potential here is just staggering. We're talking about designing life-saving drugs, creating revolutionary new materials, building AI that we can barely even comprehend. But it leaves us with this huge, lingering question. As quantum and AI finally come together, are we about to solve humanity's greatest problems? Or are we about to unlock a whole new set of challenges that we can't even imagine yet? One thing's for sure, the journey is really just getting started.